All right, this is good. All right, okay. So I'm going to talk about, and it's all about like kernel auditing stuff, right? So I spent a lot of time digging in the kernel and doing application development to kind of, we'll go into it, right? So this is me, whatever. Okay, if anybody here works at Red Hat, specifically on the code base for Audit, you probably want to leave the room if you know Kung Fu, because I don't want to get beat up. Because I'm going to be doing a lot of dissing of it. This is our blatant marketing slide. All of the research and development and the things I'm going to tell you about and the techniques is all due to my company, ThreatStack. So let's explain what the audit system is in the kernel. It basically provides you some information that is not usually privy to the user for processes and things like that. It's a passive mechanism only, which means that there's no way that it doesn't actually you can't inject or anything like that. So it's only like being emitted to you. It uses a simplistic filtering mechanism, so you can add rules to the audit system that get placed into different linked lists, and they're just basically Boolean matches, right? It can be extended by kernel in the kernel and kernel modules and that's only on the various log aspects that are exported in the kernel. Otherwise, you can't actually touch other unexported parts of the audit system. So it's really easy, like you have a kernel module and you want to start adding your stuff to the audit subsystem, that's great. So there's an application called Audit. A lot of people use it to get logs and to kind of see what's going on in their system. And people kind of assume it's just some kind of magical thing, right? But Audit and Audit are basically not, or they're mutually exclusive. So Audit is not magical. In the kernel, whenever you define a syscall, you wrap it around this macro, right? So this macro ends up eventually calling syscall define, which then eventually calls syscall multi. I really wish you guys could see this. Syscall metadata, right? And this, I'm going to explain it. It's the one that generates the code, the actual assembly code for the kernel. And what ends up happening is that every single system call that gets executed via this macro has a call for entry point and exit point that calls the function audit syscall entry and audit syscall exit. So the entry point determines a syscall that should be audited, initializes all the underlying context, the memory and stuff like that for the output. At the exit, emits several messages associated with the syscall, all kinds of crazy stuff. And after all that's done, after the message has been emitted, it sends an EOE message, basically saying that here's everything about the syscall, and it's chunked into little bits of data. So we get return statuses of syscalls. What if it was an exec VE, SOC addresses. That could be like TCP or just like any kind of struct SOC adder stuff. FD pairs, we get the PID, the UID, and the session ID. Session ID needs to be pointed out here. Basically, session ID is a atomic increment in the kernel that when somebody logs in, they will get an incremented number. And so like if you're in a different namespace or different anything that you run from your shell is still can be associated with that same session ID. The thing that you have to realize is that you actually have to have something that will go and touch a specific file and proc when you log in. So PAM will do that for you, PAM, the Pluggable Authentication module. So I'm going to blast a little bit through here. So here's some main problems and good and bad problems, right? So only one process can be doing connecting to the audit system itself. The audit system runs over Netlink, into the kernel. So you're basically just speaking directly to the kernel. So only one process can be doing that. So if you create a second process and then kill it, the first process doesn't actually, start up again. That's mainly because then the kernel would have to keep a backlog of some sort, and that's stupid. Okay, I wish you guys could read this. Okay, so this is the biggest thing that I ran into. Prior to Linux 3.8, when the audit backlog was hit and the audit log start called during scheduled timeout in the kernel, there would be a deadlock and your system would halt. So when I was debugging my application, I would get screwed, and I'd have to rush to turn off the actual audit feature in the kernel because I'd then have to reboot my machine all the time. So everything that comes from audit has this very specific format, right? It's like this key value type thing. A lot of people don't like it. I didn't like it. I thought it was absurd. But what are the alternatives? An overly complex binary messaging system, something where you have to like say, okay, this byte equals this type of message and things like that. Yeah, you're insane. You want to make it into JSON? No, we don't want to put JSON encoders in the kernel, right? So there's just simple rules that you can abide by to actually kind of like deal with the messages you're getting from the kernel. Everything in kernel is a key value. Uncoded values usually are deemed as like untrusted strings, right? And they are encoded as ASCII hex and quoted. The serial number is the kernel's way of designating a group of messages together. So if there are multiple portions of syscall that does multiple things, like it opens a socket and it's in this path and it opened up this file, then there's going to be 3 messages, and you associate those messages by the serial number. You can also do userland based messaging, but those are actually wrapped in a different thing, so nobody can like spoof a real audit message or anything like that. And they're wrapped in message equals quote and then whatever. If you're like me, stop bitching about the format and just deal with it. So here's where I start kind of getting a little making fun of stuff. So the problem with the audit stuff is that people use Audit D, which was written by Red Hat and it was written many years ago. And so we ran into problems where, it was just pegging CPU. If we had rules for like receive, for example, if when we were doing syscall, monitoring for a receive or something like that, and somebody's pounding on Nginx or your web server, you see your CPU spike up mad using this audit daemon, written by Red Hat, like I said. So it had a performance problem. It has a very limited output, format. It's difficult to extend, if not impossible, without actually going into the code. The code is impossible to read. It's poorly designed, in my opinion. Did I mention performance issues? It does. Okay. God damn, I wish you guys could see this. Okay. This is some code from Audit D, right? Like, okay, so we have a bunch of global variables and they actually say like global data. So that is always kind of like a indicator of something's going on here. Okay, and here is a piece of code that shows mutex lock and then a conditional signal to another thing. So that means that Audit D is taking every single message that comes from the kernel and queuing it up and then spinning them out in a different thread. That's bad. Because you have a lot of lock attention. Okay, so I decided to get rid of it because I couldn't stand it. So we had some goals, and these are obvious. Lower resource utilization, extend all of the logging capabilities if we, as best as we could. Try to keep backwards compatibility as much as we could. The one thing that we didn't want to do was reinvent the wheel in places we didn't have to. And abstract everything, blah, 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 so here's where we go with the low-level processing. What I mean by that is how it's handling low-level type I/O. So Audit D uses libev for signal and network netlink stuff. I use libevent and libmnl for socket for the netlink stuff, right? So once again, I wish you could see this. So the point of these basic slides is to show you, like, right, so in this slide, I'm going to kind of describe it. To create a socket and register it with the kernel and, you know, via netlink, it's very clean to do it and very easy to do with MNL. So, you know, always use something that's really good. This is how Audit D does the whole thing. I mean, there's like pages of just dealing with something that, you know, I could do in like 20 lines. So here's receiving a single message from a netlink socket with MNL. What is that? It's like, it does all the error checking, it does it all good for me. Here's netlink, right? It's crazy amounts of stuff, and you know, this is actually like 5 calls in. So now we have to, I'm going quick, sorry guys. So now we have to figure out how to deal with the data, right? So there's post-processing, which is the way that Audit D works, where it basically takes messages directly from the kernel and puts them into a log file. So you have to have an application that runs that goes and correlate, you know, does all the reconstruction of the syscalls and all the stuff that you want to do. So yeah. So like when I was talking about the serial numbers, you have, you have to do that post. Runtime grouping, which is the technique that I'm going to talk about that we used, which is to use that serial number and utilize the kernel's end of stream thing to basically say, okay, this is the start of this syscall exiting, and this is the end, and we can tie it all together. So here's this is ungrouped. It's just a bunch of lines, and I kind of put it in red. This the serial ID or the serial number. And this is how I want to do it, right? Basically like a JSON where all these things that are here are grouped into one thing. Here's some more examples, which if we had a bigger screen would be great. It's really easy to understand, like here's like, you can see a user doing a cat etho DHC client. Here's Nginx doing an open on index.html, and you get the file descriptor 13. Here's an accept for a specific IP and a specific port. Here's some ham stuff. I'll put these slides up because I feel really bad. Okay, so parsing. Parsing is a big deal because parsing can make or break your application, especially. Just to read the quote, every year, 1 out of 10 programmers will commit suicide due to maintaining parsers written in C. That is a quote from every C developer who's had to maintain a parser in C. So here's a, we have the audit method, which is basically what I call brute force, right? Here's a kind of like a grep and a word count of every single stir talk or any kind of like string comparison function. There's 448 in Audit D. I use finite state machines. Let's see how many I got. 4. All right. So I alleviate all the overhead of all the crazy like string matching stuff. So this is Audit D just parsing a timestamp. And actually looking at it now, there's actually a bug here that I just saw. It uses alloca, which the return of which could be errored, but it won't actually return null. It's here we seem to be incrementing pointers blind. Okay, whatever. Somebody who actually knows security and go look at this function, extract timestamp, and write an exploit for it. Here's the state-driven API. So the next thing that I want to talk about is how to basically turbo boost your parsing and your dealing with the data that you're getting, specifically with like conditional logic and ifs and stuff like that. So our technique, we generate a perfect hash table using the application gperf. Gperf is like a GNU program where you kind of use this key value type thing, and it fills in a structure, generates code, and fills in a structure that you can use to, a perfect hash table basically is an O1, which means that I put in a key and there are no conflicts or with the table itself, so it's very quick. And so we went and assigned known keys and values to types that can be enumerable. So I could do like switch cases on the key that normally people would be doing like stir comp or something like that on it. So in that case, we could filter out keys and values that we kind of said, oh yeah, we don't actually need these things, they're just kind of silly. We can add validation. We can determine, this is actually kind of, we can determine if a value of a key can be treated as an integer instead of a string. That's actually kind of good from a performance perspective, right? So we can do stuff like this. Once again, you can't really see it, which is not awesome. But for example, like, since and I now have enumerable types for like A0 to A like 5, which is Audit's way of saying the arguments passed to a function, I can just basically say, turn into an enum, and so it's very fast. And I can say, oh, if the value is nothing, I don't need to log it. And we can also do cool stuff like this. This is, I actually know that something is a SOC address, right? And I can try to actually decode it with a simple, one conditional, one comparison, versus most you would have to do more string stuff. So here's, and then we wanted to do, and this is really cool and it's very easy to do, is to start doing filtering post-prop, after you get the data. We use LuaJIT. It's very easy to embed in your application. There's you can do per instance or functions. So we convert the actual group data that I was talking about into a native Lua table, and we call that function. And that function can either return 0, 1, or a Lua table. 0 says, okay, pass on, you can actually log this message. 1 says, drop it, I don't give a crap. And if you pass the Lua table, it actually will take that data, morph it back into the internal structure, and then output the JSON that you put using Lua. I've already said this. So these are basic examples, which you really can't see. So here's a simple filter that says basically, okay, if it's any of these socket type functions and there's no sock adder type part included, then we don't really care about it. This one is the one that we can actually, return a table, convert it, I really wish this. Okay, so here's the output types that you have with Audit D. There's not many, you can only have one. But there is an application that comes with it. It is called Audit. So for each plugin that you write for an output, it will fork exec.ve and then start sending you messages over standard out. This is real. So that's pretty bad because, when you're reading from standard in, it's blocking and it's just creates wait states on your CPU, which is bad. And so if you want to log in some different format, no good. We end up running like a pluggable output system, and so we have all these like different outputs that you can log to. Going through this quickly again. But if you do it right, you can start adding all kinds of new types of APIs, anything Netlink related, right? So here was the actual performance test that we ended up doing, running Apache Bench at 10,000 requests per second, with rules for all kinds of like socket rules, syscall stuff. Audit D, 120% CPU. Ours, 10, which I think is pretty good. So this is the stuff that we want to do in the future. Simple analysis, statistics gathering, blah, blah, blah. So, I mean, that's pretty much it, right? Hopefully, there's nobody here, there's none of my bosses here. I want to open source this very, very badly. And I'm giving you a lot of like the techniques that we use. But if you want to tweet out something like, thread stack, please open source your stuff, all one line, hashtag, that'd be great. Because the world needs good software, not bad software. For example, OpenSSL. So that's it.
Is there any questions?
Oh, I will post them, or hey, you want a computer? Yeah, I'll post them whenever. Can you have, what's that? Yeah, the computer or the slides? Yeah, sure.
Is this part of the current first-time employee?
Yeah, it is. Mostly because we needed something that wouldn't kill the box. Any more fun questions?
Does some of the functionality overlap with dtrace, or
If I could use dtrace in Linux, I would be a very happy man. But dtrace is not native in Linux right now. Another question.
On dtrace, and there's another tool called Sysdig. Are you familiar with that?
Yes, I'm very familiar with that, yeah.
Overlap with those?
Okay, so the thing with Sysdig is that it requires a kernel module A in order to actually function the way, in order to do that kind of stuff. It's really cool, I like it, but we don't want to distribute a kernel module, or I didn't want to, but there is overlap because, and actually it does a better job in a lot of things, but not all things in the kernel can deal with, all the things that can send audit messages. Sysdig might not be able to pull that information out. But yeah, it's a really cool thing, and there definitely is some overlaps with like, tracing down syscalls and stuff like that.
So your solution doesn't need a new kernel module?
No. The audit subsystem has been in the kernel since like 2.61. Who knows? So yeah, there's no need for any kind of new kernel module or to use it. Anything else? All right. Did I get it done in the time? That was
Yes.
cool. Yeah.
Yeah,
Try to go as fast as I could.
Yeah.
All right, peace.